Hey everybody. If some kind person could just raise their hand to be sure my sound is working, I would be ecstatic. Sound check. Thank you. Thank you very much. Okay, so I'm just gonna take a deep breath and have a sip of mineral broth here before I get into this. We gotta all have, I mean, you should either have some mineral broth to get through this lecture or a very strong martini or Manhattan or a really good glass of Cabernet or something to just relax you, okay, because this is intense. All right, so let's get into it. So I've been in practice for 30 years. In the last 6 or 8 months, I have seen, it's not a worrisome trend, but it's like a catastrophic trend. My old patients I haven't talked to for a decade, all getting sick again. My new patients, yesterday, 100% of my new patients had long haul COVID. Um, Patients not getting better in the way that they ever did in the past 30 years. It's just so many layers of bad happening right now that I think we as a functional medicine community need to sort of put our heads together and figure this one out. And so I have the great privilege of having my own practice, seeing this nightmare unfold. And then in classes, we have a long haul COVID class, case almost every class in my mentorship program. So we're seeing this a lot, and it's just going to become a bigger problem. And so this is just a brief introduction to some of the key ideas we're going to talk about. I also want to very much thank Genova Diagnostics for being who they are, for being the lab that they are, for supporting the Kalos Institute and getting the word out to their folks about what we're doing here. And any of you who are Genova clients, we have a special offer coming up in a minute. I'll show you. For those of you that are brand new and this is the first one of these you've done, I'm Dan Kalish. I've been in practice since 1992, doing functional medicine. I've been teaching for 25 years. I don't know. I've devoted my life to functional medicine. I walked into a room the other day at a conference in Phoenix. It was a dinner put on by Designs for Health, and it was their scientific advisory board. And Todd Lepine was there, and David Brady was there, and Dr. Navio, we're going to talk about a minute ago, was there. And I walked in and I sat down and the wine came out and I just took a deep breath. I looked around and I was like, wow, these are my people. This is my tribe. We've all gotten old together. We all started off as young people in our 30s and now we're all pushing 60. And what's happening in our field right now is that, from my perspective, is that there's been two generations. I'm the third generation. My teacher's teacher was in the 60s. My teacher was prominent in the 80s, 90s. I'm teaching now in the 2020s. I'm the third generation of integrative functional medicine practitioner who has been dealing with chronic infections and the response to acute infections in patients and to post-viral syndromes of all types. And it's like we've been practicing for, like literally practicing, like, an athlete would practice a routine in gymnastics or something. We've been trying to get better at this for 50 or 60 years. And now we're like on stage and we're actually doing it for real because all of a sudden, a huge percentage of the population has a chronic condition. In the good old days before COVID, it took people 10 or 20 years to develop a chronic condition. Now it's happening in a matter of weeks or months at a scale which is truly epic. So we all have to get on the ball here, figure out, and my little niche in this field is lab interpretation, very specific. It's what I'm going to talk about tonight. I've done this in partnership with Dr. Richard Lord for the last 7 years. I've been with Dr. Timmons from the early 1990s, and I'm just kind of a lab interpretation person. That's what I really am good at. And you also then need to figure out other skill sets that we're not talking about tonight, whether it's coaching or clinical nutrition in general and diet and all that stuff. So we're going to just focus on this one narrow area. There's an expansion of this class in the form of a boot camp, which we are offering starting June the 8th. If you're really interested in the subject, I'd encourage you to sign up. You get a 20% discount through Genova, called using the code Genova Diagnostics 22 or GD22. And that's a 2-month class, which gets into the clinical treatment protocols that we're going to talk about a little bit tonight, but in much more depth. And like all the classes I teach, it's going to be lab review based. So we're going to review lab after lab after lab and get this stuff sorted out. Okay, so if you guys are interested, please register in that. And That long haul syndrome boot camp starting in June, next week now, is going to cover two main subject areas. So we'll get into the details on that in a sec. And I want to just talk about the biggest picture so we can at least agree on some of the mechanisms here. Mitochondrial health and how they get damaged, the ACE2 receptors, what happens there, and an understanding of the different syndromes that can happen. It could be anything from nerve pain to failure of the pancreas. We've had in the last month one case, it was, let me see, it was a father and a daughter who both developed diabetes right after they acquired COVID. In my own practice, I had a mother and her son who both had their eardrums burst right after they got COVID. I don't even know what you call that. It's like you can't even imagine. Like, was it a coincidence that they both had their eardrums burst a week or two after they got COVID? Probably not. So we don't even really know what's happening yet. But what we do know is that there's an ACE2 deficiency problem, ACE2 receptor deficiency problem, okay? And that has to get fixed in all these people. And we know that we want to be able to stimulate mitochondrial biogenesis and repair. So those are the two common problems, that whether your ears are bursting or you just developed diabetes or you have an autoimmune reaction to within long haul COVID, or you're chronically inflamed, or your back hurts, or your leg just fell off, or it doesn't really matter. Everybody at the start has an ACE2 receptor deficiency problem, and we want to be able to resolve those. And everybody at the start has a mitochondrial issue. Whether then the lungs are involved, or the heart is involved, the blood vessels are involved, or the joints are involved, that may be different for everyone. So want to get that big picture. That would be the goal of today. And then we'll look at some labs at the end of the talk today as well. And then secondary to that, just getting familiar with these terms, proteomics, genomics, metabolomics, because it helps kind of orient yourself a little bit with the testing. Those terms get thrown around a lot. It's hard to understand them. I like this image a lot. It was from a New York Times article, obviously, that just came out a couple months ago. But it's a nice picture of a person, human, right? And is there a brain problem? Inflammation and low oxygen can cause cognitive problems. Lung problem, early evidence of oxygen limitations. Circulatory system, vascular damage and blood clots can trigger fatigue. And immune system, autoantibodies or viral remnants may set off a chain reaction. So this is kind of what we're dealing with. So if there's not enough oxygen in the top of this, right, in terms of the brain, low oxygen levels, that can cause problems. And again, with the lungs, with the oxygen problem, and obviously if you have a circulatory problem, you're not circulating oxygen as well. So one of the main things that happens when your oxygen levels drop, whether it's the brain, the lungs, the circulatory system, is that the mitochondria shift their normal functioning. They change because the mitochondria are why you breathe, right? We breathe every moment because we need to get oxygen so that our mitochondria can go through the whole electron transport chain, oxidative phosphorylation, blah, blah, blah. Like that's all dependent on oxygen. So if your oxygen levels drop, your mitochondria sense that. They have little oxygen meters in them, believe it or not, and moment to moment they're reading oxygen levels. And if oxygen levels are dropping, mitochondrial behavior shifts instantly. And we need to then come along to this damaged set of mitochondria that have experienced this low level of oxygen and repair them. Because some people spontaneously repair this problem. Obviously, plenty of people get COVID and then they recover from it. But a lot of people end up getting stuck in a mitochondrial damage situation or stage. These are called CDR1, CDR2, CDR3. There's fancy scientific names for these stages of mitochondrial damage. And if you get locked into one of those stages, then you don't recover. And then you're not getting out of bed and running to the office and enjoying your best life and going out for dinner with your best friends and seeing a movie. You're in bed thinking like, why does my neck hurt so much? And I don't even know if I can take a shower today. I'm so exhausted. Okay, so we want to really look at mitochondrial repair and how that relates to these different body systems. And of course, there's other issues we're not even covering, like the autoimmunity and all that, but we're just looking at the basics. And there's a couple of models here I think that are nice. This is from this Trends in Immunology journal. I'll just show you real quick here, which again gives us some kind of map or understanding of what we're even thinking about. So we're not concerned about the people who had COVID and then recovered. Those people are out of the picture. We're concerned about those that have long COVID, either related to viral antigen persistence, inflammation, maybe a reactivation of an infection like Epstein-Barr or something like that, maybe reactive to dysbiosis, long COVID, or a COVID can trigger dysbiosis and fungal overgrowth, microvascular dysfunction, we just said that's like the microclots and those sort of problems, or some kind of autoimmune response. And this is a nice kind of schematic that we can see, gosh, you're going to have all of these different things. I've had many long haul COVID patients already who are in this autoimmune, instantly developed an autoimmune disease, like in a matter of weeks. That's crazy, you guys. How could that even happen? Like, it's crazy, you know? And of course, a majority of these people I'm working with have a horrible dysbiosis problem. We have tons of people that have reactivation of old infections. Each one of these things is playing out in different people in different ways. And you know, you're going to see some people that have overlaps and combinations of these problems, some people that have primarily one of them. Another from the European Respiratory Journal of all things, I thought they have a nice little simpler diagram here. Again, just to give us a model to wrap our minds around. Long COVID could be related to reservoirs of SARS-CoV-2, inflammation and immune dysregulation, reactivation of pathogens. I'm seeing a lot of that. A lot of people with reactivation of pathogens in my practice now. Microbiome alterations, autoimmunity, cell dysmetabolism. Now, the interesting thing about these models, and we could go on all day just looking at models, I won't bore you with that. European Respiratory Journal, Trends in Immunology. These are not like, you know, Townsend Journal stuff where it's all integrated people. This is like the mainstream science folks are starting to come over and understand things from a systems-based perspective. Now, I'm just going to mention this briefly because I think as a setup, if you guys especially get into the boot camp, you're going to need to know this stuff really well, which is that a lot of what we're talking about revolves around proteomics, the study of proteins from so many different levels. And in order to make proteins, there has to be a gene, you know, that's assembling the thing. It then has to get transcribed, this whole transcription process. And at the end of this whole thing, you end up with an enzyme or protein that has some activity. Now, ACE2 receptors are proteins. I think they have like 815 amino acids or 820 amino acids, something like that. So the whole bunch of amino acids strung together to make that particular protein. When you want to repair mitochondria, you have to repair all the enzymes that are proteins. So it turns out that understanding proteomics really matters. And then what's metabolomics? Well, when we're studying these lab tests that we're going to look at in a few minutes, we're looking at what are called small molecules or metabolites. We're measuring these metabolites to infer what's happening with the metabolism, and that's the study of metabolomics. And metabolomics, and this actually matters clinically, it's not just a kind of fancy naming kind of thing. So genomics, or the genes of the person, is going to determine, based on their overall health and what's modifying the genes, what kind of proteins they make. And then those proteins are what regulate the metabolism. And we're measuring amino acids, which tells you a lot about proteomics. We're measuring organic acids and a variety of other tests, which imply what's happening with the genes. And we're measuring metabolites primarily. So there's a lot of different levels to this stuff. At the highest level, the most sophisticated level, you can see the genes interacting with the environment. But what we're concerned about, just in the short term, let's get, you know, getting people better now kind of thing. You're worried about protein assembly and metabolism, and making sure that those systems are working well. And so you have to learn a little bit about it just so you can see clinically what you're going to do. And then if you think about the genomics or the SNPs, those are the, you know, abnormal, what do you call it, single nucleotide polymorphisms. Then I used to always think that SNPs were negative and bad, which they are when there's a patient in front of you that has a SNP that's making them sick. But then I saw this article and this whole explanation about SNPs being nature's version of trial and error. So genetic defects are nature's version of trying something new. It didn't work, and so that human being dies, you know, unfortunately in infancy, and then there's this learning process. But the genetic variations that work and the person survives are then passed on. And that's an interesting way to look at it. So we're looking at strings of amino acids, Here's our amino acids strung together. And there's 20 amino acids that make up every protein in the body except for collagen. Not that many, it's 20 of them. And you need all 20 for your proteomics to work. And so our genes are encoding for these proteins, and then the proteins are running our metabolism. Now, all this to set you up for the fact that when we talk about resolving H2 deficiency or improving mitochondrial function, the main goal is to get these things to repair, which by definition involves the person assembling amino acids together so they can heal and repair. And if you don't have enough amino acids or the right amino acids, you can't do that. If the genes are not being signaled properly, you can't do that. There's a lot of reasons why that could get messed up, and clinically, you're going to confront all of them. And any one of those things that could screw up that process will make the person not get better. All right, so let's talk a little bit about what ACE2 is and how it works, just for a moment. So SARS-CoV-2 spike protein binding to ACE2. So here's our very famous virus. Here's your ACE2, right, receptor. The virus, that spike protein fits perfectly into the ACE2 receptor. Just a fluke of bat viral bad luck that this spike protein fits right into the human ACE2 receptor. As soon as that click in happens, the virus can enter into the cell. And then the very bad news here is that ACE2 receptor, that ACE2 enzyme, that enzyme is destroyed in this process. That's the catastrophic event, because when you lose ACE2, when you have an ACE2 deficiency, a lot of really bad things start to happen, and you can trace back most of the 200 and some long haul COVID symptoms to the failure of ACE2. And honestly, I don't know that this virus is trying to destroy our ACE2. It's just using the ACE2 to get into the cells, and in that process, the ACE2 is destroyed. So when that happens, there's this whole renin-angiotensin system that gets seriously dysregulated. And when that happens, we start to have lung injury, inflammation, and leaky blood vessels. The blood vessels get inflamed, the blood pressure doesn't regulate very well, and the cardiovascular system now has a chronic inflammatory response in the people that have long haul COVID. In the acute version of this whole thing is done in a matter of weeks and the person's back to normal. But in people who lose ACE2 receptors and don't bring them all back online quickly enough, the mitochondria start to become damaged, and then this whole process plays out. So one of the first orders of business is to try to get the ACE2 receptors to come back. And there's a whole list of ways that we can do that, some of which are lab-based, some of which are just sort of generally known to science. So this is a nice little diagram. Role of angiotensin converting enzyme to ACE2 in COVID-19. And it's just kind of nice because you can see, oh, it can affect your brain. It causes the degeneration or destruction, I would say, of neurons. Neurons, it's not that the brain, this is a great quote from one of these scientists, it's not that the brain gets horribly inflamed, it's that the neurons are destroyed, they're killed, they're eliminated. So there is brain inflammation, that's a whole separate problem, but independent of that, the neurons actually are wiped out. You can't do much with a dead neuron. You can, of course, also have problems in the blood vessels, in the heart, in the muscles, all these different things. So this multi-organ injury process is happening as the ACE2 receptors are fading out. Another, from the British Medical Journal, another version of this long haul COVID thing. And I like this diagram too, again, just to kind of orient ourselves to what we're facing here. This is kind of unique in human history. Here's our virus. I really like this one from the British Medical Journal because they got ACE2 involved in the heart, ACE2 involved in the brain, ACE2 involved in the spleen and the immune system. ACE2 has to do with the liver injury. ACE2 has to do with the damage to the blood vessels. ACE2, oh, right, and so on and so on. So every single one of these problems tied back to ACE2. So in the heart, it would be chest pains, myocardial inflammation, palpitations in the lungs, coughing and chest pain, in the pancreas, pancreatic injury, pancreatitis. That could lead to diabetes, obviously. Kidney problems, gastrointestinal tract, blood vessel inflammation and vessel damage, microclots, liver damage, spleen damage, and probably the most disturbing of all these things is the 30% of people that get COVID that have a problem with their brain. So the brain uses a lot of oxygen, the most oxygen of any organ in the body. So when oxygen levels drop, the brain takes a big hit. There are a lot of mitochondria in the brain. And when the mitochondria don't do well, the brain doesn't do well. So of all these different problems, the brain fog, fatigue, anxiety, depression, this is probably one of the most concerning issues because it happens so frequently. But you can see it's all about ACE2. Why do we want to fix ACE2? And then this is like the core concept of functional medicine, is that we're not symptomatically oriented. We're underlying cause, root cause oriented. And so the root cause here is ACE2 damage. So if we fix ACE2, it stands to reason the heart could get better, the brain could get better, the spleen and the immune system could improve, the GI tract will improve. You see, this is one, it's the one to the many and the many to the one. So the one is the ACE2 that causes these many symptoms. And this one correction could potentially relieve any of these different organ systems that are under duress. And the faster we do this, the better. You certainly don't want this condition sitting around for a really long time in the person's body. So here's another kind of blow up, and we're getting into a little more detail on this. So here's the spike protein. See that here? Here's the receptor binding domain. And here's the human ACE2 receptor. So it's just bad luck that that spike protein fits right into our ACE2. And here's the ACE2 is, they show it represented because part of it's in the phospholipid bilayer there. Okay. Here's another version of the same thing, just another version so you can see what's happening here. So here's the spike protein molecular diagram. Here's the ACE2 receptor. That's that receptor binding domain thing. That's where these two connect. And then here's the rest of the ACE2, which is in the membrane. You can see these are the phospholipid bilayer that we always look at. And this is all fatty acid derived. So the membranes are fatty acids. And again, when the spike protein binds with the ACE2, this whole thing is destroyed and goes away. If you take the boot camp, I have a really good video of that. I'll show you. It's horrible. It's so horrible because they show the spike protein hitting the ACE2 receptor. It's like a war movie. It's like a World War II movie where someone's leg is getting blown off. It's just horrible. Now, in deference to my son is getting a degree now in physics at UCSF. He's starting. He's been working in the lab for a while, but he's starting his PhD in a month or two. And this is what he and his friends do. They take these pictures of stuff in a biophysics lab. So he and I talk about this all the time. But this is another diagram. This is the spike protein. This is actually what it looks like. And here's our ACE2. And they just fit together perfectly. We have to get this back. That's the first goal. If you can get this enzyme back, you can reverse the person out of all those problems, okay? And how does that happen? Genomics, proteomics, metabolomics. We're getting this enzyme back. It's 800 and some amino acids. If they're low in amino acids, it's not going to work. And then there's known and well-researched supplement products that stimulate ACE2 to come back. This is something that's been studied for a long time. I just want you to get the visual on it so you can see actually what you're doing. You need to make more of these ACE2 receptors because COVID has taken a certain number of them out. Okay, so that's step number one. Now, step number two is mitochondrial injury, healing the mitochondrial injury. And I want to talk a little bit about what's called the cell danger response. And cytokines, we're familiar with that term, I'm sure most of you, and their role as transcription factors, talk a little bit about that, and innate immunity. Innate immunity, that first step of the immune response, is regulated. I'm going to do a quiz question here. There's 200 of you on the line. Let's see if anyone gets this. What's the main sort of general or facilitator or regulator or boss or control system or initiator of innate immunity? Anybody know? I'm kind of giving it away here. It's mitochondria, okay? So now, let's look here. Robert Navio who I had dinner with a few months ago. I didn't have dinner with him. I sat next to him at a restaurant, but we did talk for a few hours. He is the most brilliant scientist one could imagine. He has dedicated his life to autistic children and understanding mitochondrial genetic disorders. And in the process of his research, he has uncovered and written quite a bit about the cell danger response. So he's well worth tracking. If you don't know of his work, just Google cell danger response and you can see what's happening there. So with just a quick quote here. Here, and this is from, forget the journal, but here we discuss transcription factors involved in the regulation of cytokines and their receptors, as well as transcription factors that are activated by cytokines. So what we're talking about here is that the byproducts of mitochondrial metabolism are regulators, and cytokines are also signaling pathways. And this is kind of strange, but let me try to show you in a graphic image what that means. And then I'll get to questions at the end too if we can, okay? So here's an image of a mitochondria. When a virus hits a mitochondria, there's an immediate change in the polarization of the membrane. When a virus hits a cell, there's an immediate change in the polarization of the cell membrane. And in response to that, the body starts to change. The mitochondria starts to shift, and rather than making energy from the oxygen coming in, it starts to make an inflammatory response. So the oxygen, instead of going to ATP production, is used to make reactive oxygen species, to create oxidative stress inside the cell. The mitochondria orchestrate this innate immune response, and one of the first things they do is they stop using oxygen to make energy, and the mitochondria go into a different mode, and they start to make reactive oxygen species. They start to create oxidative stress inside the cell to destroy the virus. At the same time, the mitochondria start to make inflammatory fatty acids, and they cram those fatty acids into the cell membrane to stiffen it up. They're ruining the cell membrane function to trap the virus inside the cell. These two things happen immediately. So the mitochondria shift the oxygen from energy production over to the production of oxidative stress. So the cell becomes toxic basically to itself, right? And they make inflammatory fatty acids and cram them into the cell membrane so nothing can get out. Now, of course, that means toxins can't get out. A lot of things can't get out. The virus is trapped in there. And as the mitochondria is doing this, all these molecules are going out are also signaling molecules. And these signaling molecules actually change DNA transcription. That's what I was trying to say before. They change DNA transcription. And if you get locked into this dysfunctional mode and there's enough inflammation and the genes change their messaging, then you stay stuck in that. And that's what Dr. Navio calls the cell danger responses. You can get stuck in CDR1 or cell danger response stage 1. You can get stuck in CDR2 or cell danger response 2. In a normal healthy person, the cells react to the virus. The cells, a certain number of the mitochondria are destroyed. The mitochondria come back, this proliferation phase, they grow back, and then they figure out how to live their lives again, and then the person's healed. So that would be the normal COVID experience. The normal COVID experience would be CDR1, cell danger response 1, this massive cytokine production, this massive oxidative stress release, damage to the mitochondrial membranes. All this is happening to contain the virus. Then after all that damage has occurred, there's a CDR2, which is proliferation. Now all the repair is happening. All these things are coming back that were damaged. And then the body teaches these new cells how to function. The mitochondria learn what their job is, and the person's healed. What we're worried about is when that normal process doesn't occur, and the person gets stuck either in CDR1 or CDR2. And you can see that on these various labs, and then you can correct for it. So if you're stuck in CDR1, it means you're stuck in this inflamed, horrific nightmare and there's damage happening. If you're stuck in CDR2, it means you have a lack of mitochondria. You have a hypometabolic state. And either of these can be detected on the labs and corrected for. And this is part of mitochondrial repair, is to assess a person based on the lab so you can fix this problem that the virus caused. I hope that makes sense. And actually, I did another talk for Genova a week or two ago where we got much more into detail on the cytokines. So if you want to learn more about the cytokines, you can go back and listen to that one. Oh, and I'm just putting this in here because it's just a study. You could read about these studies. You could read these studies forever. But this is just one, mitochondria as regulators of neural stem cell fate and cognitive function. But I just wanted to show you here that these byproducts that we usually think of as being byproducts of metabolism turn out to be signaling molecules as well. And when we look at the labs, I can explain that in a little more detail. Okay? But that turns out to be really important clinically. And also that a lot of this revolves around neurological problems and neuropathic pain. And the mitochondria, when they're damaged, they're very notorious for triggering pain. Now, here's a nice summary of what we're talking about here, which is we have the ACE2 receptor problem, or sometimes people refer to it as ACE2 deficiency or ACE2 receptor deficiency. Sometimes people call it ACE2 enzyme, but it's the angiotensin converting enzyme 2. So saying angiotensin converting enzyme 2 enzyme is kind of redundant, but I see that written up that way all the time. So the nomenclature is a little wonky, but it's ACE2 stands for angiotensin converting enzyme 2, because there's the ACE1 also, right? Also known as ACE. Anyhow, the clinical features of mitochondrial problems. So we've also seen, and these are independent but directly related, the ACE2 deficiency or ACE2 receptor deficiency, depending on how you want to say it, or the mitochondrial damage. It's the one and the other, right? Because when the ACE2 is swept away, the body starts to become inflamed, the blood vessels become inflamed, and the mitochondria are damaged. There's this rush of oxidative stress, and then this whole process is off and running. So there can be neurological problems. We already mentioned cardiac problems, gastrointestinal problems, musculoskeletal problems, eye-related problems, or general fatigue type problems, both from the mitochondrial issues and from the problems with ACE2 deficiencies. So this is another situation we're in all the time in functional medicine. You can't really tell from the symptoms what's happening. It's why we do the labs, because from the labs you can measure that. So now people always want protocols, and so here's a protocol for you. If you want, you can take a picture of this or whatever, do a screenshot. So this is a basic non-lab-based ACE2 repair protocol, or let's bring the ACE2 enzymes back. In all the patients that we're working with now, we're doing labs. So I would take this non-lab-based protocol and adjust it based on what the tests show and refine it and make it better. As I mentioned earlier, you could run this whole program, but what if they don't have enough threonine? I just ran my labs on myself. I got it back a week ago, and my amino acid profile was pretty good. It's better than I thought it was going to be. But I was low in threonine. Good luck even finding threonine, in a supplement form. Good luck. I found it. You can't get it. So if you're missing one of the 20 amino acids, you're not going to have a great time repairing the system. Okay, because remember, it's proteomics and you need all 20 amino acids. So this is a generic program that's good if you're not doing lab-based stuff, but we want to kind of take it to that next level with the labs. And then when we're looking at the mitochondrial markers, and we'll look at these labs in a moment, if you see, this is just general to give you something to get started. If you see general patterns of extremely high markers on organic acids related to the mitochondria, then you should give B-complex, carnitine, CoQ10, magnesium, and NAC. And then, of course, a multivitamin on top. If you see a hypometabolic pattern where the organic acid markers are all skewed very low when you're looking at the mitochondrial part, then you should give everything above, B-complex, carnitine, CoQ10, magnesium, NAC, and free-form amino acids and something called PQQ to start to get them to grow and to get the mitochondria to come back. And you would look at the lab and do anything else that's indicated based on the test. Okay, so these two general protocols, non-lab based for ACE2 repair and then kind of the general mitochondrial protocols that we do for either high or low organic acids markers. And we're going to look at some labs in a moment. For those of you that started late, joined us late, we have a long haul syndrome boot camp coming up next week. If you're interested and you register now, you will get a discount, 20% off if you use the code GD22. And I hope many of you do sign up. This is a 2-month class where we have a series of lectures on all these issues. We have a series of live calls where we review lab tests and get deep into the protocols and how to implement them based on the labs. And there are some non-lab-based protocols in the class and how to explain those to patients, but the bulk of the material is really oriented around how to interpret labs and customize or personalize the programs for your long-haul patients. Much better results if you go based on labs. If you're not a lab-based kind of person, then you can just do the non-lab-based programs, but then you don't have, there'd be no point in taking my classes, just look them up. The labs just change the whole world. All right, so let's see of what you're doing. So let's look at some tests and design and look at a protocol or two, and then we'll go for questions, all right? Let's see here, let me pull up the labs. I have them all queued up, but where are they? I don't know, where are they? That's a good question. There they are. Bingo. And we got plenty of time to do a program or two. Let's just start with this one and see where we're at. So this is a Genova lab, a Nutraval. Long haul COVID, what are we looking for? Well, we're looking primarily at oxidative stress, and we're looking for mitochondrial function. And there's plenty of other things that we can look for, but these are kind of like the basics that we want to cover. And so just from this cover page, there's a few things that we can see. All right, let's take a look here. Number one, okay, here's another quiz question for you. You guys ready for this? All right, I think this is the influence of my working with Richard Lord, because he just constantly quizzes me on stuff. All right, you ready? So just, close your email out for a second, pay attention, you ready? So arguably, what's the single most important nutrient in the human body, arguably? Yeah, let's just give you a little. And there's a lot of different potential answers. And see, all the students that I've been seeing all these names, Adri and Meredad and Sonal, these are all people from the mentorship class, I'm telling you, who are getting it right, okay? So I'm not saying that you should all take the mentorship, but all the mentorship students are getting this right, and everyone else is kind of scrambling. Okay, so the answer is glutathione, because if you don't have glutathione, then you can't protect your cells, you can't protect your mitochondria, and then you age and then you die. And you turn brown before they get all those age spots and you look kind of crappy and then you die. It's not a pretty thing. So this person has low glutathione. So low glutathione means that you can't protect your mitochondria. High levels of oxidative stress means your mitochondria are being damaged. Your cells are being damaged. Now remember, when the virus hits the cell membrane, the first thing that the mitochondria do is stop using oxygen to make energy, and they shift to using oxygen to create oxidative stress on purpose. And remember, they cram all these pro-inflammatory lipids into the cell membranes. Your body destroys its own cell membrane and destroys the so it can last for a little while because you can build new cells. But if you're stuck in that mode, remember CDR1, CDR2, if you're stuck in that mode, then you're stuck with oxidative stress and you're stuck with mitochondrial dysfunction. And then what happens? Well, look at that list we had. Brain problems, heart problems, lung problems, pancreatic problems, immune problems, right? That whole list of things happens when this process is left unregulated. So here's a perfect example. Long haul COVID patient with low glutathione. And then body's natural companion, the natural friend, the natural partner to glutathione is magnesium. This person is also low in. Of all the things that you could be low in with long haul COVID, these are the two absolute worst. Or you could look at it in a different way. You could say that people with low glutathione and low magnesium are prone to long haul COVID. Or you could look at it another way and say people who get COVID and in whom the COVID lowers their glutathione and magnesium are prone to long haul COVID. And we have some really interesting cases. You know, I have one in my practice. We have two in my practice now, I think. At least two, where we had all their labs done before they got COVID, and then they got COVID, and then we did their labs again. So I'm already starting to see what COVID can do to people based on these tests, because we have pre and post examples, which is pretty cool. In fact, I have one patient in my practice now, I talk about him in class a lot, where he was perfectly fine and healthy, 40s, 45-year-old guy. He's like super rich. He sold his company. He's got like $20-30 million floating around. I don't know how much money he has, but he doesn't work anymore. He's like whatever kind of guy with his money and totally healthy. And he ran a set of labs just because he was rich and healthy and wanted to see what's going on. And then he got COVID. I'm not making this up. Then he got COVID. Then he got long haul COVID. And then he redid all his tests. They have all that data. You know, you can see what a perfectly healthy, wealthy person is like with beautiful labs, and then COVID, and then trashed. It's just incredible. But one of the things that can happen is that your glutathione can drop, of course. Why? Because you're generating all this oxidative stress to try to deal with the virus. Glutathione levels are going to drop, and magnesium can go along with that for obvious reasons, right? And then the damage can happen to the cells, the cell membranes. The lipid peroxides go up. That means the lipids are being oxidized. And these are the things that we want to try to correct. So let's take a look here at the test. I hope this is making sense. I'm trying to tie this together. Oh, so for those of you that don't know, this is Genova's Nutraval. This is one of the most classic functional medicine labs from one of the most classic functional medicine lab companies. I don't know, they've been around as long as I've been around, 30 plus years of testing. And the Nutraval is one of their flagship tests, okay? Here we go. So now this is a nice blow up that'll show you the whole enchilada at one time here. So you can see from the title here, let me make it a little bit bigger. I don't know if you can see that. There, that's probably better. The title of this section of the Nutraval, Oxidative Stress and Mitochondrial Dysfunction, simply put. I mean, this was obviously created way before long haul COVID came around, but this is kind of like the test for that. So if it's yellow, well, green is good. Green means the enzyme's working, good. Yellow is not good. And red is seriously not good. And they're just color coding it so we don't have to look at the numbers here. So you can see in terms of energy production, fatty acids are not being made. You can see those two markers are both high. Pyruvic acid high, carbs aren't being metabolized very well either. And then if you look at a citric acid cycle, specifically here, check this out. Let's see. Sorry, I'm trying to get a pen together here. Malic acid is high. Succinic acid is high. Alpha-ketogluteric acid is high. And isocitric acid is high. Remember how I was saying earlier, these are metabolites. These are compounds that we use to make energy. But these compounds are also signaling compounds. So when succinic acid goes high, that leaks outside the mitochondria and outside the cell, and it signals other cells that this cell is screwed up. Let me say that again. When these markers go high, we think of them as these metabolomic metabolism intermediates, which they are, but they're also, perhaps even primarily in the case of long haul COVID, signaling molecules. So they go out and tell other cells that there's a problem here. So there's communication. When we come along with given nutrients like vitamins B1, B2, and B3, and magnesium, and we can correct this high succinic acid by providing enough nutrients that make that enzyme work properly. You can change the whole cell signaling. And the cell signaling, this is also what I was trying to describe earlier about the genomics part. So when these metabolites go high, they tell your DNA that something's wrong. So that whole transcription process, these metabolites are instructing your DNA that something's screwed up. And if that instruction gets codified or stuck, then you end up stuck in CDR1, CDR2, right? And then this whole process gets frozen in a bad, bad way. In a healthy person, of course, you get sick, these metabolites go crazy, you're feeling crappy for 2 weeks, and then the whole system resets. We're not worried about those people. We're worried about people where this system is now frozen in place. It's frozen in its dysfunctional energetics because these signaling molecules told your genes that this is the new reality and your body can't flip it back. And we can change this. It's not even that hard once you know what you're doing. You can give carnitine and that'll correct the fatty acid imbalance. You can give magnesium, B vitamins, and CoQ10, and that'll correct the citric acid cycle imbalances. And here, this person's got another problem, and I'm going to stop on this, and then we'll go to questions, okay? After I'm going to do a program first. But this is a really good example. Lipid peroxides are also high. That means the membranes, this is the membrane of the mitochondria that just happens to house the electron transport chain. If lipid peroxides are high, it means these membranes are being damaged. There's inflammation and damage occurring in the membrane. And the membrane is where you're making the energy. This is complex 1, 2, 3, and 4, and 5. These are they're embedded in the membrane of the mitochondria. And that's screwed up because there's so much inflammation and oxidative stress. So there's no way you can make energy. And these are the people who walk up a flight of stairs, you know, and a day or two later, they're still exhausted because this system is shut down. So we can fix the lipid peroxides. And let me make up a little program here so you can see how easy this can be. So and the glutathion's low. So we're going to do lipid peroxides, glutathione, and then that other stuff there. So let me see if I can remember all this at one time. I just want to show you how a program might go. So I already told you the carnitine marker was not doing well. So we're going to do L-carnitine. And then the lipid peroxides were high, so we want to do CoQ10 to fix that. So that's for the lipid peroxides. The L-carnitine is for the beta oxidation problem. And then the citric acid cycle is screwed up, so you do use magnesium also, and B complex, and then a really good quality multi. Okay, and you're off and running. And each of those is based on these lab markers. So you're taking a generalized approach to mitochondrial repair and then customizing it or personalizing it based on the person's labs. And that's exactly what we can do. And that's why you're all going to take the boot camp, because you're going to want to learn how to do that, because this is going to occupy the next decade of your lives trying to figure this out. Okay, so let me look at questions, and I'm going to go back to the beginning for the first questions here. So very much I appreciate John Ross saying Scotch. I said martini, he said Scotch. I'm on it. I'm not a Scotch drinker, but we all need the help on what kind of help we can get. Are you seeing any long-term symptoms as a result of COVID vaccinations? Absolutely, we are. Post-vaccine injury, nice phrase for it. I don't know, not hundreds of patients, but I've seen a fair number already that have had reactions after vaccines. I'm still very pro-vaccine. I think, we can vaccinate our way out of this, or we did. But I don't know how many vaccines we should all have. I've had 3, and not against vaccines, but there's a price to be paid for them, for sure. Yeah, and this will all get replayed, and you guys let's see. Let me see, recording. Any harm from adding free-form amino acids in PQQ? Yeah, you don't want to do that. Well, the free-form amino acid protocols that we use are specific to stimulate mTOR, and you don't want to do that in someone who has the high markers. So it's all dose related though. You can do it, but it's all dose related. Let's see. So Nutraval, I prefer the Nutraval with the plasma. I think the plasma testing for amino acids is more informative than the urine testing for amino acids. So I'd encourage you guys to do the blood work for amino acids, okay? Will phosphatidylcholine and phosphatidylserine help with cell membrane breakdown? Absolutely. That's one of the ways you can repair cells, cell membranes, is with those particular nutrients. If you're adding a good quality multivitamin with good B vitamins, can you skip B complex? Yeah, but the multivitamins I use don't have enough Bs in them for what we're trying to do, because you need to get at least 100 milligrams of thiamine to make a difference. You need to get at least 100 milligrams of riboflavin to make a difference. So they have to be pretty high dosages of B vitamins for this particular situation. So I don't think most multis are going to have nearly enough on the Bs, okay? You can use combination products, but usually then the dosages aren't high enough, you know? Let's see. So now, let me show you here a basic protocol. I think I had it. Yeah, so here's a non-lab based, just what you should be taking protocol. Curcumin, lipoic acid, N-acetylcysteine, D, butyrate, omega-3s, CoQ10, and resveratrol. For a variety of different reasons, each of these is either going to help ACE2 receptor repair, or mitochondrial repair, or both. And if you then want to take it to the next level, then you can look at the high markers, the low marker patterns. Individual nutrients can be brought up. So if, for example, you've got a non-lab based person and you want to give them some, I don't know, what's an example? N-acetylcysteine, or let's say CoQ10. I mean, how much CoQ10 are you really going to give them? You know, like, I don't know. Generically, 100 milligrams, 200 milligrams, you don't want to screw people up. You can't give them a super high dose. But if you do a lab test and you see their CoQ10 levels are really low, I mean, you could easily give them 400 milligrams of CoQ10 based on the lab, or maybe even 800 milligrams based on the lab, but I would never do that without a test. So if you're not using the test, you have to keep these dosages really conservative, because you don't want to harm anybody. You can't go to a high therapeutic dose without a lab to know that they need it. If their glutathione levels are low, for example, you could easily give them 3,000, 4,000 milligrams of N-acetylcysteine to bring up their glutathione. Not forever, but just until you redo the test. So that's just another consideration to make, okay? Is that the labs allow you to develop much more effective programs. Let's see if we have any more questions here, then we're gonna wrap it up. So I think I answered the CoQ10 dosage one. I think we covered most of these here. Yeah, okay, good. All right, we're gonna wrap it up right on time. I wanna thank you guys for participating. And I hope to see some of you in the Long Haul Syndrome Bootcamp. If you're interested, come check it out. You get 20% off, 2-month class, lots of lectures, lots of special bonus stuff, lots of lab interpretation time put into this, so you guys can really, get familiar with these protocols, okay? Okay, have a great rest of your week, everyone, and we'll see you soon.